welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Jarkko Peltomäki. He's going to speak to us about the repetition threshold for ternary rich words.
Sure, thanks, Narad. And this is joint work with James Curry and Lucas Moll. And here's a short table of contents that I will introduce to you to the problem of these repetition thresholds for each words. And I'll tell you something about what's been known before our results. Then I will outline the result or the proof of the result we got. And then there's been some more progress since that, so I will tell you something about that. So I guess everybody knows what a critical exponent is, but here's the definition. So the critical exponent of an infinite word is just the supremum of the exponents of factors that occur in the word. And here I'm today talking about a repetition threshold of a language of infinite words. So let L be a language of infinite words. So its repetition threshold, RT of L, is then the infimum of the critical exponents of the words you have in that language. And yeah, and just as an example, if you put L to be the set of Sturmian words, then I guess it's pretty standard knowledge that the least exponent you find in that set is 2 plus the golden ratio. And this infimum is actually achieved by the Fibonacci word. It has this critical exponent. And in the recent years, it's been somewhat popular to compute these repetition thresholds for various interesting classes of words, like episturmian words or balanced words over more than 2 letters. Papers like this. And but today I will talk about the following problem, which is about determining the repetition threshold for the language of rich infinite words over a k-letter alphabet. So we would like to know this quantity as a function of the number of letters you have in the words. And of course, I'll tell you what a rich word is. So now in this definition, we're talking about finite words. So a finite word U is rich if it contains its length plus 1 distinct palindromes as factors. And I include the empty word as a palindrome, which accounts for the plus 1 here. For example, I have this binary word 001, 0110, and you can check that it contains these palindromes. And there is 8 of those, which is the length of this word plus 1, so that word is rich. However, if you append the letter 0 to this word, you don't introduce any new palindromes, so this set of distinct palindromes still stays the same, but the length increases by 1, so this word is no longer a rich word. And actually, it's a pretty neat exercise to prove that whenever you append a letter to a word, you can introduce at most 1 new palindrome as a factor. So it just means that this length plus 1 bound here is the maximum you can achieve. I mean, that's the reason why they are called rich words. They are rich in palindromes. And an infinite word is simply rich if all of its finite factors are rich. And some examples of rich words, like rich infinite words, include Sturmian words and their generalizations. Like you can generalize Sturmian words as episturmian words. They are still rich. That's actually one of their defining characteristic. And also another way to generalize Sturmian words are these codings of symmetric interval exchange transformations. They are also known to be rich. By the way, it's usually not that trivial to prove that an infinite word is rich. So all of this information requires some work to prove. Whereas it's easy to check that the Thue-Morse word, for instance, is not a rich infinite word. Okay, but we're interested in the set of rich words over a certain number of letters and the least critical exponents you expect to have in those words. And this problem was actually raised by Jethro Vesti in 2017 or so. So he asked this question in one of his papers. And he did the, I guess, pretty natural observation that for the upper bound, so it was already known by that time and long before that Fibonacci words, which are generalizations of the Fibonacci words, they are certain episturmian words, that they are rich, and we knew how to compute their critical exponent. So actually, the critical exponent of the Fibonacci word is this number, where phi k stands for the generalized golden ratio. So that at least gives an upper bound for this quantity that we're interested in. And you should note that this upper bound tends to 3 as your number of letters goes to infinity. And then there is a result by Pelantov and Starosta from 2013. So they proved that every infinite rich word contains infinitely many overlaps. So overlap is just a factor of this form, where A is a letter and X is a word. So you have a square followed by a single letter. So you get a repetition that's a bit over 2. So you have infinitely many factors like that. And that in particular means that this repetition threshold is always strictly greater than 2, no matter what your k is. So this is kind of some sort of first observations about this problem. And then in 2019, Baranwal and Shalit, I think they were not directly thinking about this repetition threshold, that problem, but a bit of a related problem. They exhibited a rich binary word that had a critical exponent of 2 plus square root of 2 over 2, something like 2.7. I mean, less than 3, which was kind of the bound that you would expect from Vesti's observation. So they got this upper bound, and then they also conjectured that this bound is optimal. I suppose they did some backtracking searches and couldn't find anything lower than this, and hence they made this conjecture. And a bit later, Curry, Moll, and Ramprasad did prove that this conjecture is true, that the repetition threshold in the binary case is 2 plus square root of 2 over 2. And they actually give some words that achieve this lower bound. I will show later in the talk what they look like. Okay, so this is what's known about this problem up to 2020. And of course, you would like to know what's the answer in the ternary case and beyond. And what we did with James and Lucas is that we proved what the repetition threshold is in the ternary case. And it so happens that it is this number where mu is the unique real root of this polynomial. It's something like 2.26. So we know that value now, and in fact, to determine this result, we actually proved a certain kind of structure theorem for all ternary rich words that avoid 16/7 powers. I'll state it in a second. Yeah, and before I can state this structure theorem that explains what do the rich ternary words with low critical exponent look like, I need to define some morphisms and a transducer. So for this talk, you don't really need to remember what these morphisms are, but there are two morphisms that are quite short and simple. And then there is a transducer tau, which is a bit more complicated. So the way you read this is that each letter has two possible images. And when you apply tau to an infinite word, you use the left image on odd positions and the right image on even positions. So it's not a morphism, but a transducer with two states. And the only difference between these left image and the right image for all of the letters is that you change ones to twos. Otherwise, they are the same. So you have an alternation of ones and twos if you apply this transducer. And this is the structure theorem. So if you let Z to be a ternary infinite word, which is first of all rich, and moreover avoids 16/7 powers, then it takes a specific form. So what our theorem essentially claims is that after you remove some finite prefix of Z, you can decode it in three steps. So first you can decode it with tau, with this transducer. It will decode it to another ternary word. That word, in turn, you can decode with this morphism G. And that word you get after decoding with G, you can decode with F n times for as large n as you like. Additionally, you might need to permute the letters at some point a bit, but that's kind of beyond the point. But what follows from this theorem is that because this morphism F is primitive, you see that whatever Z you have that obeys these conditions has all the factors of this word, which is the fixed point at 0 under F, and then you apply G and tau. That infinite word, all of its factors are found in Z. So it means that the critical exponent of Z is at least as high as the critical exponent of this infinite word. So deriving the repetition threshold then amounts to proving that this infinite word indeed is rich, and its critical exponent is this number, which is the repetition threshold for three letters. Yeah. And I guess that covers all the significant results from our paper. So the rest is just proving this structure theorem. And the thing is that it's quite technical, the proof. So it's something like 20 pages of quite technical observations. We use a lot of computer searches, backtracking, things like this to check if some factors are unavoidable. So going through these details doesn't really make up a really nice talk, but I will just a bit sketch how you would start to prove this structure theorem. So I will sketch the part to see how you could desubstitute. How do you prove that you can desubstitute the word with this tau? Then you need to show the same for G and the same for F, and this F proving it for this, this inner morphism F. That's the trickiest part, but I'm not going to go into those details today. For that, you need to check the paper. Okay. So as a starter, we assume that Z is a ternary rich word that avoids this 16/7 powers. The 16/7, I guess it's just just a convenient number that's a bit bigger than the actual repetition threshold. Nothing special about it. And what we would like to show is that after you remove a prefix of Z, it takes this form. And then this is pretty much what you would expect from a paper in, avoiding powers. You use backtracking searches. So the first step is that you look at these three factors, which are permutations of each other. And you check that if you have a word that avoids these powers and is rich and avoids these factors, it only has length 388 at best. So you know that the Z, because it's infinitely long, has to have one of these words as a factor. And without loss of generality, we can assume that Z has this word as a prefix. And then I included this short, simple lemma, which states that this Z cannot contain either of these factors 1, 2, or 2, 1. And this is a nice, simple exercise in using properties of rich words. So proving this is something like, well, suppose on the contrary that 1, 2, or 2, 1 occurs, and then let P be the shortest prefix of this word Z that ends in 1, 2, or 2, 1. And then denote by S the suffix of P of length 2. It just means that S, the suffix, equals 1, 2, or 2, 1. And because of the way we define this prefix P, the reversal of S cannot occur earlier in our prefix P. And this then in turn implies that the only non-empty palindromic suffix of this prefix P has length 2. I mean, if there was a longer palindromic suffix for P, it would have as a prefix a reversal of S, and we just kind of argued that that's not possible. Okay, but then on the other hand, we know that P has this word as a prefix. So every word of length 1 already occurs in P before this suffix S. And this in particular means that this longest palindromic suffix, which has length 1, occurs multiple times in this prefix P. And that's a problem, because you can prove that rich words have the property that the longest palindromic suffix of a rich word is uni-occurrent, which means that this longest palindromic suffix has only one occurrence in that rich word. And then since this is not the case for P, we see that P is not rich, which is a contradiction. So we have this lemma. And then I'll continue a bit. So, okay, maybe I'll go back a bit. If you look at the images of the transducer tau, you see that they all begin with 0, 0, and 0, 0 doesn't have any other occurrence in these images. And all of these images end with a letter that's not 0. So it makes sense to factorize this Z according to occurrences of 0, 0 if we would like to de-substitute with tau. So it's natural to look at complete first returns to 0, 0 in Z. A complete first return to 0, 0 is just any word that begins with 0, 0, ends with 0, 0, and contains exactly 2 occurrences of it. And clearly 3 zeros in a row does not occur because that's a cube, and that's too much. And we may focus on returns that begin with 0, 0, 1. I mean, you also need to prove the result for the returns that begin in 0, 0, 2, but that's pretty much the same proof as what I'm going to give here. So we just want to determine all the complete first returns to 0, 0. And the way we do it is by brute force, basically. We just extend 0, 0, 1 in all possible ways and exclude certain continuations as we go. So for instance, here I wrote the 3 extensions of the word 0, 0, 1. If I continue with 0, that's fine. If I continue with 1, then there is a backtracking search that shows that any word that has the properties that we're looking at with this prefix has only length 498. So eventually we will run into a problem. If we did continue with the 2, then we would have this factor 1, 2 that we just proved not to be there. So there is only one way to continue 0, 0, 1. And then kind of keep doing this. If you add one more 0, then you actually found a complete first return. We're done. This is the image of 0 under this transducer tau. If we add 1, that's fine. If we add 102, then there is again a backtracking search that shows that eventually there is a problem. And okay, I wrote all of this here, but I mean, as you can see, they are of pretty, the reasons why we exclude something are pretty simple. This word has 2.5 power as a suffix. That's a no-go. There is that forbidden factor again. You keep going. And eventually you find this word, which is a complete first return to 0, 0. So you do these baby steps, and you realize that the 0, 0 has two complete first returns that start with 0, 0, 1, this factor and this factor. And then you do, I don't think it's, maybe it's not a completely analogous argument, but a similar argument at least. You do it for 0, 0, 2, and you find that all the complete first returns are these two words in that case. And this is pretty much as far as I'm going to take this today. But what you would need to do next is to, because we want to desubstitute with this transducer tau, you also need to know what kind of first returns to 0, 0 can appear next to each other, and you need to forbid certain kinds of configurations. But you can imagine that it's more of the same, that if I have these two returns next to each other, then I have maybe too large of a repetition, or a backtracking search shows that it's not possible, things like this. But this is this is how it goes, or how you get it started, and then it just gets more complicated. But yeah. Yeah, okay, what's here? Oh yeah, yeah, I mean, the structure theorem is one part, but the other part is determining what is the critical exponent of this infinite word. And here is just some remarks about it. So it's, the thing is that if you have a morphic image of a fixed point, then there is a kind of a standard way how you would determine the critical exponent. You know that the long repetitions are more or less morphic images of shorter repetitions. So you have a finite seed set of repetitions that generate all long repetitions. And pretty much the same happens also in this case. But since our word is not a morphic image, but there is this transducer, there are some, let's say, complications. So for instance, I wrote here that there is a problem with odd periods. So 0, 0 is a square. It has an odd period of length 1. But if you take its image under tau, it's not a square. It's this word. So because in even positions you apply tau in one way, and in odd positions in another way, you have this alternation of ones and twos. So not all exponents are preserved when you map with tau. So there are some extra steps you need to do when you determine the critical exponent, but I don't think there is anything, let's say, noteworthy about what's going on. And yeah, that's, I guess, all I want to say about our paper. And then I'd like to end this talk with some remarks. And I guess the obvious question is that what is then the value for the repetition threshold for the 4-letter case? The thing is that I don't know. I don't have any candidate word what that would achieve this. I did some backtracking searches and which suggest that the correct value is around 2.117, but that's pretty much as far as I've gone with this 4-letter case. So that's that. And then I want to end this talk by talking about the related problem, which concerns this notion of asymptotic critical exponent. So here's the definition of the asymptotic critical exponent of an infinite word, but it's just a lim sup version of the usual definition of a critical exponent. So it just means that you still consider the same quantity, but you exclude finitely many short periods. So you're looking at the asymptotic behavior of the exponent growth, not from the beginning. And then you can ask the analogous question about asymptotic repetition thresholds for a language of infinite words. And in particular, you can ask what's the asymptotic repetition threshold for K-letter rich words. And it was recently published, the proof by Dvorakova, Klauda, and Pelantova, that this asymptotic repetition threshold for rich words always equals 2, independent of your alphabet size. It's a nice result. And not going to talk too much about their paper, but there is essentially two ingredients to proving this. First of all, you would, or yeah, two points that they prove from which this follows. So they find a morphism sigma k over which generates a k-letter word or a k-letter rich word, and moreover, this word that you get from this morphism has to have the property that the asymptotic critical exponent tends to 2 as the alphabet size increases. So that's what you want to find. And the second is that you want to project it to the binary alphabet. So actually you can already find on a binary alphabet, you can find rich words whose asymptotic exponent is arbitrarily close to 2. That's what they in fact proved, yes. So that's the rough idea what's going on. And on the next slide, I will actually give explicitly what this morphism sigma k and this projection is. So this is what they look like. So this, now I actually seems that I used the wrong letter, but this is supposed to be sigma. So sigma k always maps a letter. I mean, the image is always 0 followed by the pre-image plus 1, except for the final letter, which takes this special form. So all of these initial ones, the images have length 2, and this has length 3. And the projections, how you project this k-letter word to a binary word, is simply that each letter I you map to 0, 1 to the power I, no matter what I is. So that's that. And the reason I wanted to give you these morphisms explicitly is that there are some interesting observations Dvorakova and Pelantova have made. So first of all, there is this earlier proof by Curry, Moll, and Rampersad that determines this repetition threshold in the binary case. And it so happens that it's achieved, this threshold, by this word. So you take a word on a 3-letter alphabet and you project it to binary. So it happens to have that form. And I guess this is the reason why Dvorakova, Pelantova, and Kloda figured out these more general type of morphisms. But moreover, there is another recent preprint where Dvorakova and Pelantova show that our word, so this word that achieves the repetition threshold in the ternary case, it's actually of similar form than this as this word. So if you take on a 5-letter alphabet the fixed point of this sigma morphism and you project it to not to the binary alphabet but to the ternary alphabet via this map where these A, B, C, and D are given here, you get this word. So in fact, I mean, I've been talking all the time kind of in a way that having this transducer here is necessary, but Dvorakova and Pelantova showed that it is not. So this word is a morphic word, but it seems that the price you pay when you remove the transducer is that you now need to work on an alphabet of size 5. So we didn't really try to see if any of our proofs are easier if you use this form instead of this form, but I think they are. My guess is that they are both equally horrible to work with. And yeah, that's actually all I wanted to say today. So thanks for listening.
Thanks a lot, Jarkko. Does anyone have any questions? Hajime.
We're not hearing you.
So sorry, I was muted.
Yes.
Thank you for nice talk. And so I have a question between the difference of RT and RT stir. So do you have sufficient conditions such that the so RT is not equal to RT star?
Sorry, can you repeat it?
For example, in the case where for Sturmier word, so RT stir is equal to RT, is it right?
Yes.
So is there sufficient conditions such that the RT is not equal to RT stir?
Yeah, I mean, it can happen that they are different. I mean, okay, I need to fight with Zoom, but as I said, in the binary case, this result here, if you look at the proof, it shows that you can find this this asymptotic critical exponent E star as close to 2 as you like. But if you just consider the critical exponent, so without the star, it has to be at least 2.7 or something like that. So there are for sure examples where it's different.
So it's an example. So my question is sufficient condition or sufficient and necessary conditions.
I don't know about any such conditions. I mean, I haven't thought about this, so no idea really.
Oh, okay. Sorry. Thank you. I'm sorry. My question is vague.
Yeah, no worries.
Thank you.
Thanks.
Jeff, did you have a question? Oh, Gabriele says in the chat, 1 is to be a fixed point of a uniform morphism.
Okay. Thank you.
Sufficient. Jeff, did you have a question?
Yeah, I was just wondering whether there's any hope to prove that this number for alphabet size k is going to be the 0 of a polynomial of degree k or something like this.
Yeah, I mean, I don't know. But like this, what's here on this slide, it kind of suggests that, I mean, from this you could conjecture that the thresholds are related to these sigma morphisms, and if that's true, then for sure they are the critical exponents are. I mean, what did you say? But I mean, roots of
Well, algebraic numbers, let's say.
algebraic numbers of or roots of certain polynomials, because in the paper where these morphisms sigma are introduced, these critical exponents are explicitly computed and they come from pretty simple polynomials. Yes.
Thank you.
So what was the question in chat?
Oh no, Gabriele was just pointing out that one sufficient condition for Hajime's question was for the word to be a fixed point of a uniform morphism.
Okay. Live and learn.
Luca.
So hello to everyone, and thank you very much for your talk, Jarkko. I can't see Edita, so I just want to react because, of course, it's a problem that is very much interesting for us. I would like to mention that we have a conjecture. We recently, so we have this conjecture, in fact, that you mentioned, Jarkko,
Okay.
the behavior for KI alphabet of any size, that it is going to be similar. We would like to start collaboration with anyone who can help with this problem, because we can see that there are like 2 points, not only to find the right candidate, but also to prove that it is the minimal one, that it's the optimal one. So there is still really much work to do, very exciting work maybe. So we can discuss this then in Nancy probably afterwards.
Yeah, I'm looking forward to that discussion. I mean, as you say that there is 2 parts, and I guess that proving an upper bound, like finding the suitable projections and figuring out the critical exponent, that's maybe the easier part. But then how do you
and then to prove the
minimality?
optimality? Yes.
Yeah.
So this is one point. So and and then I would like to fix something which concerns epistolarian words. So please, Jarkko, can you go back to the result by Vesti to his bound?
Okay. Where this one?
I would like to mention something, because we with Edita Pelantova recently we have published a paper on repetition threshold of epistolarian sequences, epistolarian words, and in in connection with this topic, I was going through old results of people concerning Fibonacci words, and I can see that so Vesti, when he says that the critical exponent of Fibonacci sequence, Fibonacci word is this value, he cites the result by Glenn and Justin. But when looking at their paper, I could see that at that time, the term critical exponent was used for what we call now asymptotic critical exponent.
Oh,
So
really?
yeah, really. So you can check it in the paper by Vesti and also the paper by Glenn and Justin that they were able to determine the asymptotic version, the asymptotic critical exponent. And this is why in our paper with Edita, we determined the critical exponent. It is the same, so there's no change, but it was necessary to do this also. So just to fix this, if you want, you can check that, of course, if you don't believe it, because it's quite natural that the critical exponent, the minimal critical exponent is reached for the Fibonacci word, but it was necessary to prove this.
Okay. Thanks for pointing this out. I didn't really know that there is
Yeah,
a
I think that almost nobody knows, and I was also surprised when I checked the results then.
Yeah, and I mean, I must say that your paper where you determine this these least critical exponents for epistolarian words and asymptotic critical exponents as well, I thought it was done like years ago.
Years ago, yes, yes,
So
you are
I
right.
didn't.
So
So
everyone thinks.
yeah, so I'm happy it's done now, and the answer is what I thought it was all these
Yeah,
years.
yeah, yes. So just this.
Yeah.
So thanks once more.
Does anyone else have any questions? Okay, if not, thank you again, Jarkko.